Another approach is to compute the probability using this formula commonly given with Bayes' theorem. So for example 4, remember that interpreting medical results, assume cancer has a 1% prevalence rate, meaning that 1% of the population has cancer, denoting the event of having cancer by C, which is we have the probability of having cancer is equal to 0.01 for a subject randomly selected from the population. And this result is included with the following performance characteristics for the test for cancer. Probability of cancer is 0.01, where there is a 1% prevalence rate of cancer. The false positive rate is 10%, which is 0.10, meaning that the positive test result given that cancer is not present. The true positive rate is 80%, which is the positive test result given that cancer is present is 0.80. Now again, finding the probability that having cancer given that a positive test result. Again, find the probability that the subject actually has cancer given that he or she has a positive test result. So this was our table that we had from the previous example. We had the positive test results, had a total of 107, 8 had cancer, 99 had no cancer. Negative test results, we had a total of 893, 2 had cancer, 891 had no cancer, and then there's the total of how many had cancer and how many had no cancer. So by using this other approach, we're going to be using Bayes' theorem. Bayes' theorem is the following. The probability that B occurred, provided that A has already occurred, is equal to the probability of event A times the probability of event B, provided that A has already occurred, divided by the probability of A times the probability of event B, provided that A has already occurred, plus the probability of the complement of A times the probability of event B, provided that the complement of A has already occurred. Now, what we're going to do is we're going to replace the letters for A with C, and replace B with positive, and where P of C and P of the event positive, provided that the complement of C are given. So here's what's given. The probability of cancer is 1%, always known as 0.01. The probability of the complement or not having cancer is equal to 1 minus 0.01, which is 0.99. Now, the probability of having a positive cancer test, given that you have cancer, is this 8 out of 10. So it's 8 out of 10, which is 80%, 0.80. And the probability of having a positive result, provided that you do not have cancer, is going to be 10%, which is equal to 0.01. So we're going to plug those values into the formula. So here's our formula. We replaced B with C and replaced A with positive. So we know the following. We know that P of C is equal to 0.01, and we know that the probability that it is positive, provided that you have cancer, is 0.80. And then we want to find the probability of C, which is 0.01, times the probability of positive, provided that cancer is given there as that value, plus, and we want to find the probability of the complement of cancer. So the probability of not having cancer is 0.99, and then we're going to multiply that by the probability of having a positive result given that you do not have cancer, which is 0.10. Okay, and let me go ahead and correct that number over here, that this should be 0.10. Okay, so now what we're going to do is, if we multiply that all out, then we get the following. We get the same result in our previous example, and that previous example up here gave us that 0.0748, which is at 7.48%. So therefore, we would say the following. When 100 physicians were given the information, 95 of them estimated the probability of cancer, given that you have a positive test result, to be around 0.70 to 0.80. So they were wrong by a factor of 10, because that means that you can see that the factor of 10 is the difference between those two. Now, physicians are extremely intelligent, but here they likely suffered from confusion of the inverses. The given rate of 80% for positive test results among those who are true positives implies the probability of having a positive result given that you have cancer is 0.80. But this is very different from the probability of having cancer given that you have a positive test result. So physicians would have done much better if they had seen the given information in the form of a table.